The second law of thermodynamics states that the total entropy of an isolated system will always increase over time, implying that processes occur in a direction that leads to disorder or randomness. Actually, the second law of thermodynamics explains that in any closed-off system, things tend to get messier or more disordered over time. It's like saying if you have a neat room and don't tidy it up, it's likely to become more chaotic on its own. This idea applies to the way energy and matter behave in the universe.
Thermal energy reservoirs. Thermal reservoirs are large systems capable of giving or receiving an infinite amount of heat without undergoing a significant temperature change. They serve as reference points for temperature in thermodynamics and are often used to model the heat exchange in various processes. There are 5 concepts of thermal energy reservoirs. First, two-phase systems and furnaces. The statement explains that two-phase systems and industrial furnaces can be modeled as reservoirs capable of absorbing and releasing significant amounts of heat while maintaining constant temperatures. And the second is reservoir size not strict. It emphasizes that a body doesn't need to be large to be considered a reservoir. It depends on the ratio of the thermal energy capacity to the transferred energy. The third one is potential benefits of waste energy. Properly designed and managed waste energy can improve marine life by controlling temperature increase in bodies of water within safe levels. Next is heat transfer concerns. The transfer of heat from industrial sources to the environment is critical, as irresponsible waste energy management can lead to thermal pollution, disrupting marine life. Last but not least, source and sink definitions. The terms source and sink are introduced categorizing reservoirs based on whether they supply or absorb energy in the form of heat.
Next, we go to the Carnot refrigerator and heat pump. The table here shows the comparison between the Carnot refrigerator and Carnot heat pump. First, Carnot refrigerator is a hypothetical cooling device that operates on the principle of the Carnot cycle. Meanwhile, Carnot heat pump is a theoretical device operating on the Carnot cycle. Next, Carnot refrigerator absorbs heat from a low-temperature reservoir and expels it to a high-temperature reservoir. On the other hand, Carnot heat pump is designed to move heat from a low-temperature reservoir to a high-temperature reservoir. The third difference is, Carnot refrigerator is functioned to maintain a low temperature inside the refrigerator while expelling heat to a warmer environment. Meanwhile, Carnot heat pump functions to heat a space using an external energy source even when the outside temperature is lower than the desired indoor temperature. And finally, Carnot refrigerator is an idealized concept, and real refrigeration systems have limitations due to factors such as friction and irreversibilities. On the other hand, Carnot heat pump is an idealized model, and real heat pumps have practical limitations.
Carnot refrigerator and heat pump is basically the same device. They operate on reverse Carnot cycle. The direction of heat and work interaction are also reversed, and also focusing on the cooling device. For the heat flow for the refrigerator, the heat from food absorbed and released to the outside of the refrigerator. And for the heat pump, the heat with low temperature from outside to the high temperature place like the interior of the building. And for the COP or coefficient of performance, for a refrigerator assesses the proportion of heat taken in from the cold reservoir to the energy expended in eliminating that heat. For the heat pumps, the COP for a heat pump gauges the relationship between the heat supplied to the hot reservoir and the energy invested in transferring that heat. For the refrigerator, COP equals to 1 over QH over QL minus 1. And for the heat pump, COP equals to 1 over 1 minus QL over QH. And QL represents the amount of heat absorbed from the low temperature medium. And QH represents the amount of heat absorbed from the high temperature medium. The COP is very crucial in assessing the efficiency of reversible refrigerator and heat pump. The COP quantifies the effectiveness of a refrigeration system. For reversible system, we can leverage absolute temperatures of high and low temperature reservoirs to evaluate COP. COP calculation involves the heat transfer ratio. So, to enhance the accuracy, we replace this ratio with absolute temperature ratio. In the case of reversible refrigerator, we substitute the absolute temperature to find the COP. This method provides a more comprehensive understanding of system efficiency. And similarly, for the reversible heat pump, the same approach is applied. The absolute temperature plays a very important role in determining the COP. The absolute temperature provides a more accurate reflection of the system performance.
Refrigerators to preserve perishable food have long been essential appliances for household. They have proven to be highly durable and reliable, providing satisfactory service for over 15 years. A typical household refrigerator is actually a combination refrigerator freezer, since it has a freezer compartment to make ice and to store frozen food. The amount of energy consumed by refrigerators can be minimized by practicing good conservation measures. One of the good conservation is clean the condenser coil located behind refrigerator, cool hot food to room temperature before put into refrigerator, check the door gasket for air leaks, open the refrigerator door the fewest time possible for the shortest duration possible, don't block the airflow around the refrigerator coils, turn on the power saver switch to stop condensation in humid place, avoid excessive ice sprayed out on the interior surface of the evaporator. Lastly, avoid unnecessary low temperature setting.
So from the question, we get the value of TH is 298 Kelvin, net work done is 500 watt, and the COP refrigerator is 4.5. So for the first thing, that question 1 is QH from refrigerator space. By using the definition of COP, which is COP is equal to QH over work net, we substitute the value COP and work net that we get from the question. So we get the QH value is 135 kilojoule per min. For next, we will find the temperature of the refrigerated space. Use the formula COP is equal to TL over TH minus TL. We substitute the value COP and TH. We will find the value of TL is 243.818 Kelvin. From the question, we can get the info of TH is equal to 1173.15 Kelvin. TL is 300.15 Kelvin. T at refrigerated space is 268.15 Kelvin. And QH is 800 kilojoule per min. For the first thing, that question 1 is QH at max refrigerator space. First, we will find the thermal efficiency. So when we substitute the value of TL and TH, we get the answer is 0.744. Then, from the value of thermal efficiency, we can find the value of work. So we substitute the thermal efficiency and a QH. Then we get 595.3 joule. Then we use the COP formula at Tref. So we get the answer is 8.37. Then the last step is we use the COP formula to find Qmax. COP is equal to Qmax over work. Then substitute. We get the answer is 4,982.6 kilojoule per min. For next, we will find the Q heat reject to ambient air. First, we will find the value of QL by using the formula QL is equal to QH minus work. Then we get the answer 204.7 kilojoule per min. Then from the value of QL, by using the same formula, we can find the value of QH source. So for the last step, we use the Q rejection then equal to QL plus QH formula. Then we substitute, we get the answer 5,782.7 kilojoule per min.
A summary for these two subtopics. The first one, thermal energy reservoirs, crucial in Earth energy balance, include oceans, the Earth crust, and the atmosphere. Oceans absorb and release solar radiation, shaping climate patterns. The atmosphere, through processes like conduction and radiation, acts as a thermal reservoir with greenhouse gases regulating heat retention. Understanding and managing these reservoirs are essential for addressing climate change and developing sustainable energy solutions. The second one, Carnot refrigerator keeps things cool by taking heat from inside and sending it outside. Now, a Carnot heat pump does the opposite. It takes warmth from outside at low temperature place like the air and pumps it inside at high temperature place like your room, making the inside warmer. Both work on a cycle and have efficiency limits determined by the temperature they deal with. That's all from us. Thank you.